Okay, so yesterday we talked about NBOBs, normal mobs, and we talked about continental flood basalts. We talked a little bit about this, and we saw that there were distinct rare earth variations, and we were trying to figure out what could be the mantle. How did the mantle produce this diversified melts? Now, today I will bring back the topic at the end of it, but at the moment I think what we should go into some of the isotopic systems that were developed early in the previous to in the last not before 2000. These isotopic systems were developed, and they contributed greatly to our understanding of the mantle. So we will talk about this today, and we will be talking about two systems. One is called the rubidium-strontium system, and we will be talking about the samarium-neodymium systems. But first we will talk about what about general equations that we can derive from isotopic isotopes, and then we will switch over to first rubidium and then samarium neodymium, and then we will combine them to see how did the mantle contribute to this tremendous amount of basaltic volcanism that the crust is composed of. Now, the basic equation to this comes from this very famous relationship that was experimentally determined. dN by dt is proportional to n. Essentially, dN is the number of parent product, and t is time. So essentially, it talks about the rate of how the parent product would change is directly proportional to the number of parent product. It is something like this. So if you have a system where you have time elapsed, and this is the number of parent nuclide. So once you start with a particular number of parent nuclei died in zero, you know that this decays with time, and so the decay curve is something like this. So essentially, it is something like this. Now, the important aspect of this curve is that once you have half the number of products gone, and this is zero, half the number of products gone, then this happens at a particular time, and this is called T half. This is called the half-life of the isotopic system, which means the mass of the parent isotope is reduced to half the numbers. Then you have the other half. If you divide it, then it reaches here, and you have T 1 by 4. And then again, if you divide it, so this is T half 1 by 4, and this is 1 by 8. So you have T 1 by 8. So this is called the first half-life, for example. First half-life. This is called the second half-life. And this is called the third half-life, and so on and so forth. I just took out a value from a book, and this is for carbon dating. This is 5739 years for carbon dating, which we are not interested here. 5739 years, that is when half the mass is disintegrated. It takes 5,739. And then, of course, it is 11,460 years is what it takes. And then the third half-life is 17,190 years. So that is how the total time required for disintegration into first half-life, second half-life, and third half-life is achieved. So this is how, and you can see if I take any point here, and draw a tangent to this. This is the variation of dn by dt. And you can see as you move down the curve, the slope changes like this. So the slope, the rate is not the same. At infinity, of course, it is almost the same as equal to negative 0. So all the slopes are essentially negative. And similarly, if you look at the dotted products, they also, of course, they increase, and they increase like this. So this is how the concentration of the daughter nucleides, they change. So this is how the system works. So it has a negative slope, it's steeper, close to the parent product where it is equal to its initial value, and then finally the slope changes, decreases the slope. So what happens in the derivation, therefore, this dn by dt is then written as dn by dt, and then you have a proportionality constant which is called lambda, and then you have n, and you produce a negative value because of the negative correlation between dn and n. So that is the basic equation that is used. And so from there, you can derive this relation dn by n is equal to minus lambda dt. Now we consider the lambda as independent of temperature, independent of time. So the lambda is independent of time. And if we integrate this relationship from n0 to a particular value of n, and you integrate this from time t is equal to 0 to a particular time t is equal to t. If you do this integration, then the integration of this becomes ln n by n0 is equal to minus lambda t. Yes, minus lambda t. Now this equation is quite an important equation from which several important derivations can be done. So we do the first derivation, that is all of you know it from your school, and that is n by n0. If you take the half-life, then n by n0 should be equal to half. So it is ln 1 by 2 is equal to minus lambda t, or you can reverse this and you can write ln 2, this is half-life, so ln 2 divided by lambda is equal to t half, and this value is 0.693 by lambda is equal to t half. So this is time unit. So lambda, you can see, is time inverse. So that is what it's all about. Now, this is one equation which we don't use a lot, but people who do experimental work on decay equations, they use this equation very strongly, right? So this is one of the equations that comes out from this very relationship. ln n by 0 is equal to minus lambda t. The other equation that can be derived, and that is important for us, is this. Here we can write n by n0 is equal to e to the power minus lambda t from this equation, and from this we can write n is equal to n0 into e to the power minus lambda t. This is what we can write, e to the power minus lambda t. Now, since in the total number of the daughter and the parent remains the same, so we can write if n0 is equal to daughter plus parent, and this is n0, then we can write p is equal to d plus p into e to the power minus lambda t. This is P because this is the remaining parent, and this is daughter plus parent. So, and we can write therefore P into e to the power lambda t, P into e to the power lambda t minus P is equal to D. Or if you reverse it, then we can write D is equal to P into e to the power lambda t minus 1. Now this is a relationship that is very much used in people who deal with isotopic systems. What does it say? That if this is the daughter product, then after the time elapsed, t, after a particular time, the number of daughter products, daughter nucleides, you can find out, if you know the time, decay constants are almost always known. So if you have an idea of the time, and since decay constant is known, you can find out the daughter if you know the amount of product in the cell. So this is a very, very famous equation that you can actually quantify the number of daughter nucleides if you know the number of parent nucleides initial plus E lambda t, the elapsed time minus 1. This is the equation. So now once we do this, I will write this equation at the top so that we can use it later. D is equal to P into e to the power lambda t minus 1. And the other equation, I will just write it, 0.693 divided by lambda is equal to t half. Remembering that we will be using this equation more commonly as we isotope people do. So this is now an important aspect here is the following. If you have, I don't know whether you know it, but maybe some of you know it, that, in the field of nucleosynthesis or in the field of stellar nucleosynthesis, that means all the elements after hydrogen and helium, they were nucleated, some were nucleated in the stars. They formed in the star because of what is called, I don't know if you know this, this is called binding energy curve. And this is nucleus. Then the binding energy curve is like this. This is the peak at 56 ion. Now, according to this binding energy curve, say for example, if you have A disintegrating into B, for example, or for a reaction A plus B is equal to C, C will be stabilized if the free energy of C is less than A plus B for the particular pressure temperature condition, and this is what happens to the binding energy curve. So here in this, you can see if you follow this curve, this is the nucleus. There are more nucleons. The number of nucleons increases on this side, nucleides increasing on this side. So what this binding energy curve does is, the binding energy curve increases in steps. I'm not going into the details. And then there is a peak that follows, and then there is a drop off which follows, and this goes up to 207, 235 length. So this takes care of all the elements that is there in the periodic table, including its isotopes and reference elements. Now what happens here? In this, you can see the heavier nucleides. Let's say I take a point here. I take a point here and I draw this, and I take a point here and I draw this. So what happens here, you can see the heavier nucleides, in other words, if you look at the binding energy curve, the one that occurs after in this part of the curve. Okay. The heavier, this is the direction of increasing nuclides. So the heavier nuclide has the one with the lower binding energy than this one. So what happens, when you talk of nucleosynthesis, or in the stars, for example, the nuclides are brought together and they are fused because as they break the Coulombic barrier. So here, according to this, heavier nuclides become more stable by reaction or disintegration through the integration of the elements with lower nuclides, lighter nuclides. So this is the area of what is called fusion reactions. This is where the fusion reactions occur. And the peak is at 56 iron, which is the peak of the nuclear binding energy curve. In this you can see the heavier nuclides are more stable than the lighter nuclides. But if you come to this place, then you see that the heavier nuclides have a lower binding energy than the heavier nuclides, which means that if it has to, here for example, then this possibility is just the opposite of the fusion reaction. Here fission reactions occur, just because of the shape of the binding energy curve. So F56 iron is the line of division between fusion reactions and fission reactions. Here, two elements in fusion reaction, two elements are fused to produce a new element. Here, one element is disintegrated into two or more elements, and they are this is what is called the fusion reactions. Now, most of the fusion reactions that occur, or all of the fusion reactions that occurs within stars. Within stars. So they form well inside the stars. And once they form, they produce heavier and heavier nuclides. And many things becomes possible, but one thing is important, that some of the stars become so dense inside that they undergo what is called supernova explosion. The limit of it was found by a very famous Indian scientist, S. Chandrasekhar, and he told us, and he showed us how stars of particular mass above that, you have supernova explosions and neutron stars and formation of black holes. So now all of these fusion reactions normally happen within the stars, but fission reaction, they occur outside the stars. Outside the stars. They happen, this type of reactions happen when, say for example, a star that is formed and you produce all materials of fusion reaction and the gravitational collapse occurs at the core of the star and this part is blown off to gain momentum, to conserve the momentum. So what happens? This is what happens to the supernova, that the outer field is blown off and the inner field collapses because of the very new gravity. So this ultimately converts to what is called either a neutron star or very famous black holes. Today, there is a lot of research in the cyclotron based on the black hole formation, etc. Whatever that is important. So when this supernova explosion occurs, when a star has the mass and has produced the density, it explodes. And so what happens? All the heavier materials that are there already outside, occurring as a rim inside the core of the furnace where fusion reactions are occurring, they move at relativistic velocities, at the velocity of light. And when they do, because of the reactions that occur here, a lot of neutrons and protons are produced. At the last stage, where black holes are last stage of supernova explosion, a lot of reactions happen where both neutron and proton are thrown off at the same speed as the heavier elements do. So what happens? There is a lot of interpolations and bombardments as soon as the supernova explosion occurs. And most of this occurs in a few milliseconds of the supernova explosion, because material starts to move away and the distances between them increase, and so there are less and less collisions. But important point is that you have a lot of neutron and proton flux when this supernova happens, and these neutrons and protons react with the already existing heavier nuclides that were produced during fusion in the stellar interior. They are bombarded. So what happens is, if you plot all elements, if you plot all the elements, say for example, if you take this as neutrons and you take this as protons, if you have a graph and you plot all naturally occurring elements, then this is the line where the number of protons is equal to the number of neutrons. If you draw a line with the number of protons equal to the number of neutrons, but if you draw what is existing, the concentrations of the protons and the number of protons and the number of neutrons, then you will see the graph looks like this. Graph that you produce of the number of protons and the number of neutrons are like this. So what happens to the graphs? If you take all the naturally occurring elements and their isotopes and you plot it on the number of neutrons and number of protons, then number of neutrons into number of protons, this is exactly what happens. That means all naturally occurring elements are dominantly neutron rich. These are all dominantly neutron rich. Why? It is because, and this deviation, first it follows the x, this proton is equal to neutron line. But at a particular value, it starts to diverge. And this occurs at the point where you have iron. You remember, I just told you that iron and iron group of elements, like iron, chromium, nickel, etc., these transition elements, they form as the last stage of the fusion reactions. And till that stage, the number of protons and the number of neutrons is the same. But as you go to the heavier elements, they are all proton rich. So this is because, say for example, you have an existing nuclide here. Say I draw a nuclide here. So if during the supernova or immediately following the supernova, the few seconds where the supernova occurs, there are neutrons, these can be bombarded by neutrons. These can be bombarded by neutrons. And if they are bombarded by neutrons, then the number of neutrons increases this way. Whereas if they are bombarded by protons, if the bombardment of protons, then of course the number of protons increases this way. Have you understood? So if you have a heavier nuclide here and it is bombarded by neutrons, then the nuclide becomes neutron rich. At the same time, if they are bombarded by the protons, then they become proton rich. So basically, proton rich nuclide should be here and neutron rich radii should be on this side. This is what happens. Now when you do this, I hope you get it, because if there is more neutrons being bombarded, then these becomes neutron rich radionuclides, and if it's bombarded by protons, then they become proton rich nuclides. Right? If you do that, then there is a problem. Why? Because in this graph that I have drawn, there are areas, if you can look it up in internet sites or in books, there is a zone in the middle. There is a zone in the middle. Here in the middle, there is a zone. these are all stable elements. All stable elements. They cluster inside this cloud of elements, or in other words, these are all unstable elements. All unstable elements. These are all not elements, nucleides is the better term. Stable nucleides and unstable nucleides. But because, and these are stable nucleides. So whenever you have a neutron bombardment, it takes the heavier nuclei, it takes the pre-existing nuclei in this direction. In this direction. And if there is proton bombardment, it takes the heavier nucleides in this direction. But when you make it neutron rich, they are very unstable. And they would like to go back into the zone of stability. They would like to go back to the zone of stability. And those which are proton rich, they also would like to somehow reach back, come back to the zone of stability marked in red. And so therefore, this neutron rich and proton rich radionuclides, they do something, and this is what is called radioactivity, where they find out natural processes in which to go back home. The home is the red lions, the red card. They always try to go back home by using processes called radioactivity. Now, I must tell you at this point, see, when you bombard an existing radionuclide by neutrons, neutron is electrically neutral. So if it's electrically neutral, but protons are electrically charged positive ions. So if you look at it even commonsensically, then you will see that bombardment of neutrons is a much more prominent and dominant mechanism that would be allowed than being bombarded by a proton, simply because the proton will be facing a tremendous amount of repulsion. But neutrons will not be experiencing this amount of repulsion. Have you understood? So, that is why neutron-rich radionuclides are common, but proton-rich radionuclides are uncommon, simply because proton is electrically charged, and therefore attachment of protons, successive protons in the nuclide is not well tolerated. But neutron-rich radionuclide does not require this. So they became electrically neutral, and therefore the elements are all neutron-rich. All elements, say for example from 56 iron, you see this line is called the mass number because it's the number of protons plus number of neutrons. So till here, where you have 56 iron and the transition group of elements, they have values close to x is equal to z. Here, here the number of neutrons are much more than the number of protons. Only here, the neutrons and number of protons are the same. So what happens is, because of the supernova explosion, the nuclides that form due to fusion reaction within the stars, they are thrown out, and as are the large number of neutrons and protons are thrown out, and this process here by which it forms is called the E process. E process, I can't go into details, this can be discussed very much, but E represents equilibrium process. So whatever it is, so the attempt of the nuclei, naturally occurring nuclei, is to go back here home, and the proton-rich nuclei, if they are permitted, they would like to go back home. It's about going back home. Radioactivity is a natural process that allows an unstable nuclide to go back to its zone of stability. So, and what are the processes? So that is important. What are the processes? And here we see this. I will draw it with the same axis. There is nothing conventional about it. Just because I have drawn neutrons and protons in this way, So I will now let's say this is neutrons and this is proton. And let's say this is N and this is P, and this is the parent. Let's say you have a parent here with N number of neutrons and P number of protons. Now what happens? You know that there are three radioactive processes. One is called beta decay, that is the emission of an electron. Then you have electron capture, in which the nuclei captures an electron, and you have what is called the alpha particle decay. So these are the three natural processes of disintegration, or which is called fission reactions. Not fusion, fission reactions. So what happens during beta decay? Let's look at this. Beta decay is the loss of an electron. That's all what it is. Loss of an electron. So if it's a loss of an electron, a neutron becomes a proton. Isn't it right? If there is a loss of an electron, then a neutron converts to proton. So essentially what we have is N minus 1 and P plus 1, because the number of protons increased by 1 and the number of neutrons decreased by 1. So this is the process of beta decay. This is beta decay. Essentially, emission of an electron would make a neutron to become a proton. So one neutron decreases, one proton increases. One neutron decreases, one proton increases. This is the method for beta decay. Now you go to electron capture. The moment you do that, an electron capture, you can see one proton is converted to a neutron. Electrically, it becomes electrically, one becomes electrically uncharged. So here you have N plus 1, P minus 1. Have you understood? So one proton, if you admit an electron, so the electron comes in, reacts with the proton to produce a neutron. So P reduces by 1, neutron increases by 1. So you have N plus 1 and P minus 1. And this is called electron capture. So these are the pathways of radioactive emissions. And then you have finally proton alpha particle decay. What is an alpha particle decay? It is the emission of 2 protons and 2 neutrons. Emission of 2 protons and 2 neutrons. So if you do that, you take this part, and this is N minus 2, P minus 2. So that means this part is this direction. Remember, it's at 45 degrees. To the same scale, it's 45 degrees. So this is N minus 2, P minus 2. This is alpha particle decay. Have you understood? So now, we can go over to rubidium strontium, but just before that, in order to conclude what I was saying. So, if you have neutron bombardment with neutrons, that means your radionuclides are going this way. This is what is beta decay. Have you understood? Look at the graph here. This is beta decay. So, the elements that have suffered neutron capture or neutron bombardment, they go back to their zone of stability through beta decay. So the graphs look like this, or like that. What is the difference? Here, a lot of neutrons are attached, but there is one beta decay, and then a lot of neutrons are captured. So this is what is called a R process. R process stands for the term rapid accretion, rapid bombardment. So you have a neutron capture, a beta decay, and again neutron capture, and a beta decay, and a neutron capture. So this is a very, very fast process. Have you understood? So it takes you this way and up. But here you have one neutron capture, one beta decay. One neutron capture, one beta decay. One neutron capture, one decay. This is called an S process. Slow process. So what happens? You bombard it with a neutron and this undergoes beta decay. Bombard it with neutrons, beta decay, and so on. So both are going simultaneously, where you bombard it with a lot of neutrons or it's a slow culture. And beta decay, and more neutron, and a beta decay. Or you have a lot of neutrons and a beta decay. So all things can happen. But essentially, it takes the whole thing on this side. The direction of it is on this side. So that is how neutron-rich radionuclides come to the zone of stability by beta decay. And you can see here very well from the diagram now that electron capture, this process, would be adequate to bring proton-heavy nuclides into the zone of stability, because that vector is this way. So proton-heavy nuclides, which are much less common than neutron-rich radionuclides, they go back to the zone of stability by what is called electron capture. But at the same time, you have also alpha particle decay. You know the trajectory is this direction. So this is the direction of alpha particle decay. This is the direction. Not from here downwards. It can't take you back. But from above, you can go through it by alpha particle decay. Alpha particle decay has the trajectory like this. So alpha particle decay brings you also from unstable zones to stable zones to stability fields, but the trajectory is like this. Whereas beta decay, the trajectory is like this, and electron capture is this way. So this is what happens due to radioactivity. Right. So we had digressed a little bit from the main topic, but now I think we will go back to the main topic. Now, important point is, rubidium, strontium. Rubidium has several isotopes, radiogenic and non-radiogenic isotopes. Strontium has several isotopes, both radiogenic and non-radiogenic isotopes. Out of which, here we talk about a particular decay equation in which 87 rubidium disintegrates by beta decay to 87 strontium. That's all what we are talking about. We are talking about 87 rubidium, which is the parent, disintegrates into 87 strontium, which is the daughter. Right? Now all of you have, I think, have studied this, so I will push the whole thing through. I think you have known, but I thought maybe I will say it a bit before we go into the main diagram. It helps you to get a more little bit of cohesion. So you have 87 rubidium to 87 strontium. This is the decay equation that we are talking about. We are not talking about other isotopes. Now what happens when you do this? So initially when you start, say for example, if you take the Earth, when the Earth accreted, and there is a lot of discussion of this accretion, etc., it's a completely different topic. I can talk for maybe 2-3 hours, so another person who is a specialist in law would have a full semester to talk about it. But there is a lot of problems of what happens to the isotope during accretion, and that's a major point of debate now. So what happens is, simply looking, when the Earth formed, condensed from the gases, when the minerals accreted to form the Earth from a cosmic gas at that time, the Earth inherited, it had some 80s, at the present moment, if you take the 87 strontium value, it has two parts. One is the 87 strontium that the Earth inherited, plus the 87 strontium that it acquired by beta decay of 87 rubidium. So this 87 strontium is called the initial or inherited. Here we talked about inherited, just to make it that this was then found out then at the time of the Earth's accretion. And then you had 87 strontium that formed due to beta decay of this. So if you take the total about, this is the strontium that you measure now. This is the strontium that you see in rock. You pick a basalt and you would know, okay, this is 87, this is the amount of 87 strontium now. So now this 87 strontium is equal to 87 strontium initial plus 87 strontium that you acquire by decay, and that is the equation that you use. What? So how much of 87 strontium? So parent is 87 rubidium into E lambda T minus 1. 87 rubidium is equal to this. Now what happens? We divide this normally, 87 strontium by 86 strontium. And now 86 strontium is non-radiogenic. It's non-radiogenic. That means it has not changed its concentration since the Earth acquired, it has not changed its concentration. So if we divide this whole equation by 87 strontium by 86 strontium, so you have 87 strontium by 86 strontium initial plus 87 rubidium by 86 strontium into E lambda T minus 1. That is how the famous reaction is. You have seen this equation many times. So this is the very important equation that you have. Now this is divided, 87 strontium is divided by a constant number. 86 strontium does not change. It does not change, which it does not change its abundance since it formed. So 86 strontium is divided like this. If you do this, then this equation can be written as y is equal to c plus x into m. It's a straight line equation where y is the measured 87 strontium by 86 strontium. This one is the intercept as it goes, and x is 87 rubidium by 86 strontium, and E lambda T minus 1 is the slope. So if I do that, so I can take my x value here as 87 rubidium by 86 strontium. This is it, increasing. And here we have 87 strontium by 86 strontium, 87 strontium by 86 strontium if we plot. Then say for example a rock which has say minerals A, B and C. A, B, C, C, B and C. So it has more amounts of C, A and B. So since this ratio does not fraction it, must fractionate, all the elements will have the same value as 87 strontium by 86 strontium across all minerals. So you have mineral A, mineral B and mineral C, and also some A, B and C, and somewhere is the composition of the rock itself, because the total isotope ratio would be dependent on the proportion of A, B and C. So this is at time t is equal to 0 when the rock formed. But as time elapsed, 87 rubidium disintegrated. What happened? The point A started to migrate in this direction, in the direction of decreasing 87 rubidium by 86 strontium and increasing 87 strontium by 86 strontium because of the decay. So it decays, and finally at this point this is the equation of a straight line, so they lie on an equation, but time t is equal to t. So this angle would depend on the total amount of time elapsed. Total amount of time elapsed, and they should be lying on a straight line. From this straight line, you can find out 87 strontium initial, you can find out as a part of the intercept, and also you can find out this term, E lambda t minus 1. So that is the tangent to this. If this is theta, then this is tan theta is equal to E lambda t minus 1. So now from this you can find out, if you take it, ln tan theta plus 1 is equal to lambda t, and therefore t will be equal to ln tan theta plus 1 divided by lambda. So this should give you an idea of time. So two things are important. One is the time that elapsed you can find out from time t is equal to 0 to time t is equal to t. And the other thing is you can find out is the 87 strontium, 86 strontium initial value that you need to find out. For this, the most important thing is you have to consider the system as a closed system. As a closed system means there had been no exchange of isotope ratios across the system surrounding interface over time. There are many ways to do it, but we need to ensure that the system behaved as a closed system. This we need to ensure. So what happens is, we can see that now that we can find out the initial concentration of the element, and we can also find out time t once these are on a slope, and we can find out the tan theta, and we can find out the slope. This is what is the basic equation to 87 strontium and 86 initial E lambda t minus 1. That's the basic equation. So if I tell you that what would be the equation for, say for example, samarium and neodymium, they have a product-daughter relationship. And they have, samarium is also several isotopes, and so does neodymium. But the important point is, 147 samarium, this disintegrates to 143 neodymium, and you can see this is an alpha particle decay. This is an alpha particle decay. And we do this, if you do this, then writing with this, can you look at the similarity here? And therefore, and we normalize this 143 neodymium by 144 neodymium, which is a non-radiogenic element. This is identical to 86 strontium. So if we look at samarium neodymium value, samarium-neodymium ratios, it is given like this: 143 neodymium, 144 neodymium is equal to 143 neodymium divided by 144 neodymium, and this is initial, plus 147 samarium divided by 144 neodymium into E lambda T minus 1. It's basically a similar equation. Right? So it's 143 neodymium by 144 neodymium, 87 strontium by 86 strontium, and 144 neodymium is non-radiogenic. So its concentration does not change. So this is the equation for samarium and neodymium. Remember, between samarium and neodymium there is only one element in the rare earth, and that is promethium. And that is promethium. So you can understand, if promethium is the only element that separates samarium and neodymium, therefore the masses of this isotope, mass difference of this isotope will be very, very small, much smaller than rubidium and strontium. So obviously you need greater accuracy to measure these ratios. But whatever it is, what we can see is 143 neodymium. We have two systematics now, one for rubidium strontium and one for samarium neodymium. Right? The only important thing that you should remember at this point of time is that over time 87 rubidium decreases and 87 strontium increases. Here 147 samarium, which is the parent, decreases and 143 neodymium increases. And time t is the elapsed time for all. Okay, I think I will stop here. We will continue in the next class. And I hope to finish it in this next class. Thank you.